I come from the University of Cyprus, but I also come from somewhere very local, from this startup company called Argument Theory in Paris. So from the audience here, how many of you know about argumentation? Comme ci, comme ça. Okay, good. All right. So because the title is one thing, the content will be another. Yeah.
So it seems you are sharing the presentation screen, so you might be weird for people online. So you're sharing the
Yes.
presenter screen, not the. So they can see the timer, but I guess it's okay.
No, I want to share the screen because then afterwards we do a demo through the screen. Okay. So how do we go to the next one? So this talk is about, at the end you see, is about argumentation. But the motivation is more general. The motivation really is, how do we do reasoning in AI? How do we do problem solving? Reasoning just means problem solving to me, okay? Because you reason to a conclusion, you reason to a decision, you reason to a solution. So how do we do problem solving in AI? And there is this question that everybody now is addressing because of the hype of LLMs. Can we use LLMs for reasoning? Okay. But really, it's not clear how much reasoning we can rely on LLMs reliably. And the question is, should we use LLMs for reasoning, or should we use them for what they are good at, which is natural language processing, information retrieval, or in another way, shall we train LLMs to reason, or shall we connect LLMs to reasoners? Okay. And this, of course, you might recognize as a kind of neurosymbolic approach. Now, but whatever reasoning there is or there isn't in LLMs, whether you like them or you don't like them, or you believe they have and they don't, if they have any reasoning, that reasoning has to be human reasoning in natural language. There's nothing else it can be, all right? But, and believe me, this is what we'll be talking about. Human reasoning in natural language is argumentation. The way to formalize, the way to understand human reasoning in natural language is argumentation. Okay? That's why, as I said, this talk will be really about argumentation, about its foundations, but also about argumentation technology for problem solving. Okay? As we said, we're interested in problem solving, and we're interested really in problem solving from specifications, if possible, that come in natural language. You take the document and you generate a solution to whatever problem that document describes, the requirements or whatever. So this talk is going to be about argumentation. When you finish with this talk, when they ask you, do you know about argumentation? You say, yes, I know very much, and I know how to get more information about argumentation because I can give you the slides and the references, and you become an argumentation expert yourself. But despite the fact that you're already argumentation experts, why? Because you're human reasoners, and humans reason in argumentation. Okay? So that's the main focus. And if we have time, I'll tell you about argumentation in machine learning and argumentation in ethics and AI ethics. Okay, so let's start with argumentation. History. The history of argumentation starts from Aristotle, and probably before. Over the millennia, it's been studied in many, many different areas. Okay, it's not something new. What is new is that we see it in the last 30 years more prevalent in AI studies. Okay. the kind of AI thing started, it boomed up in the early 1990s. So it's something it's been studied very much in the humanities, philosophy, cognitive science, behavior economics, and things like this. And one of the tasks, and I'll say from now, of the AI, if you want to do good AI, you should link with these studies. You shouldn't just take it as an engineering problem. You should take it as a wider problem. And all these studies show how argumentation really is native to human reasoning. Whether it comes from philosophy studies, there is these people are French, Messier and Sperber. You may know at least Sperber is a very famous professor in cognitive science. Does anybody know him? Yeah. Okay, and they write, and they've got this paper, Why Do Humans Reason? They have a recent book called Enigma, The Enigma of Human Reasoning. And the whole point there is that reasoning is equated to argumentation. Behavior economics, and in AI, there was a lot of discussion in old AI where we were trying to find non-monotonic logics. Who has heard the term non-monotonic logics? Okay, good. Yeah, I expected that because it's kind of more a French thing as well as other things. And in the early 90s, it was shown that all non-monotonic logics and reasoning can be reformulated within the same framework of argumentation. Okay, so this is kind of the brief history of argumentation. And now let me give you some basics, the bare minimum basics, and you don't need really much of argumentation so that we can build the rest of the talk. So what is an argumentation framework? How do we formalize argumentation? It's very simple. We have a framework or an arena where we do the argumentative reasoning. It's made out of three components. The first component is these argument schemes, which are basically associations between some information, premises, onto some other statement, a position or a claim or a conclusion or an option when we're deciding. But these are loose associations. These are not logical rules in the sense that premises holding must necessarily, we must necessarily have the claim. The licenses or topai, as Aristotle says, for arguments. Then we have some notion of conflict between these arguments, between these schemes, okay? That conflict can come from the language. We have some form of negation or some form of conflict in the language, or it can also come, the conflict therefore can be at the premises, at the position, or it can actually come also a conflict on the actual link, all right? So, and then we also have, this is one binary relation which is normally symmetric on the argument schemes, and therefore the arguments that we build from the argument schemes. The schemes, because they're parametric and you can just fill in the parameters with specific values and you get a specific argument. This is one symmetric relation that tells you when arguments attack each other, when one argument is a counter argument to the other. And this is, again, another binary relation on the schemes and on the arguments, which we call defense, and which, in a sense, captures the strength of an argument relative to another argument. So an argument A can defend an argument B, we will see, against an argument B, if it's at least as strong. And we'll come to that in a moment, okay? It's not, what happens when we do in argumentation, we have the arguments conflicting each other, and sometimes one has sort of stronger status that says, okay, you are a counter argument, but I can't defend against you because I am at least as strong or stronger than you. If you're weaker, then you cannot defend. We will see that in a little bit more detail in a moment. Okay, so once you have this machinery, which is general and abstract, Then what you need to decide, what you need to define is what is a good argument, or what is a good set of arguments that build a case for the position or the conclusion or the solution, right? And Aristotle tells you in his first sentence of the topics books, which is the specific set of books that study argumentation. And he says, well, he says, you have to sustain your argument. What does it mean, sustain your argument? It means defend against the counter-arguments, because if there's no counter-arguments coming from the audience or from the environment, you don't have to do anything, okay? You have to defend against the counter-arguments, and you have to avoid saying anything self-contradictory. So in other words, the way you defend your arguments should not be self-attacking. And this is the formal notion of what is a good argument. Actually, you need to generalize it a little bit. You need to have this kind of relative recursive form of acceptability and say acceptable arguments are those that render relative to them all their counter arguments non-acceptable. So this is a nice recursive definition, which can be formalized in proper mathematics through an operator and through a least fixed point of this monotonic operator. We don't need to go into the details, but just this operator is the standard thing that says an argument delta is acceptable with respect to another argument delta prime, either if it's a subset, which means this is the context under which I'm reasoning, or for any attack there is a defense, and that defense is acceptable with respect to the original context delta prime union delta. That's why I'm saying the arguments delta become acceptable by rendering their counter-arguments non-acceptable, which means finding the counter-argument in alpha, finding a way that we defend against alpha acceptably. So the least fixed point exists, and the acceptable sets of arguments are those which are acceptable relatively to the empty set, because you don't want to. Okay? Yes.
How do you establish the existence of the fixed point? Are you going to talk
Yeah,
about
because this is a monotonic operator. On the set, it's a very simple. It's a monotonic operator on the relations between things. It's a very simple thing. Okay, and you take the least fixed point. Okay, so schematically, this is what you do in this fixed point. Okay, if you end up where you have an attack that is equal to some defense, you can't show, it won't be in the fixed point. You need to generate in defenses that have new attacks, and if you generate such a branch where all the defenses belong to each other on top, then you're acceptable. And then what you do once you have this notion of acceptability, but think of it simply that you can defend against counterattacks and you're not self-attacking, all right? If you have this thing, then the way you reason is you find such a case, acceptable case of arguments that supports your conclusion. That's a plausible or possible conclusion then. And if you can show that there is no acceptable case set of arguments that supports any contrary conclusion, then that's a skeptical conclusion, because there's no possibility for having an opposing solution. All right, opposing option. Okay. Now I'm going to stay with the foundations, because it's very important to pass on this message that argumentation, the theory that we've seen there, which is a very simple theory, and basically is a theory of a fixed point operator with least fixed points, all right? No monotonic operator, least fixed point, is enough to capture all forms of reasoning that we know. It is in fact enough to capture classical logic. that you know about. The classical logic, predicate calculus is called, or propositional calculus, right? So you can actually, we call this argumentation logic. So this argumentation framework, when you apply it on the language of classical logic, or here we only talk about propositional logic. When you apply it on the language of propositional logic, we call it argumentation logic. And it can give you classical logic equivalently in a boundary case, and then it can expand smoothly into other realms, for example, into the realm of inconsistent premises where classical logic collapses. Okay. Let me give you the hint of the proof. The hint of the proof is the following. What are the argument schemes? So now I've got to construct propositional logic as in terms of argument schemes, conflict and defense. And the semantic notion of acceptability is the same. I'm not going to touch that. All I have to do is just give you these building blocks. All right? The argument schemes are proof rules. You take the proof rules. Think of, I guess everybody in France knows about natural deduction in propositional logic, yes? Proof rules. You cannot take, though, the proof rule of introduction of negation or reduction ad absurdum or proof by contradiction. Okay? You take the standard proof rules like modus ponens. You have premises, and these premises give you conclusions. And obviously, you take these proof rules and you say, look, you can't attack. Remember when we were talking about being in conflict, you can't attack the link. You can attack the premises. You can attack the conclusion in the usual propositional logic case of negation, but you can't attack the link. This modus ponens is modus. Once you have one, you have to have the other one. Okay. Good. The conflict is this symmetric thing. You take two sets of arguments. Now, because we said you can't attack the links, in a sense, the arguments schemes, we can map the argument schemes into sets of formulae for the premises, right? That might be a little bit difficult to grasp, but let's say the arguments are just sets of formulae for the premises. I forgot to say there is another argument scheme, which is the hypothesis scheme. So you can hypothesize any formula you like. The attack is just that if you put them together, you get a contradiction, negation contradiction. But you derive this only using these definite proof rules. Remember, we've taken proof by contradiction out. And the defense is simple. A formula can defend against this negation and vice versa. And formulae which are in a theory are stronger than formulae of hypothesis. Okay? They're a very natural thing. If I'm given some premises, those premises are stronger than hypotheses as arguments, okay? And arguments which together give me a contradiction attack each other. And I can always choose between a formula and its negation. Okay. Once you do this, to recover then full propositional logic, what do you need to recover? You need to recover the proof by contradiction, but you've taken it out. Okay, and the proof from contradiction comes for free by that acceptability, recursive acceptability semantics that I approach. What is proof by contradiction in argumentation? Is an argument which has an attack, which needs to be defended, and that a new attack the necessary defender. Then this argument is not acceptable. This formula is in contradiction All right? Is not acceptable. The difference, of course, with, and this is what gives you the equivalence of the two logics. The difference, of course, is that with argumentation logic, if you assume that a formula is not acceptable, that does not mean that its negation is acceptable. It only means that if your premises are consistent. If your premises are inconsistent, you can have a situation where a formula is not acceptable and its negation is not acceptable. This is the classical case of paradox. But argumentation logic does not have any paradoxes. Exactly because it gracefully allows this situation to happen. Okay? So no Cretan Epaminondas coming out shouting, I am a liar. It can come out, it's not going to impress argumentation logic. Say, okay, we all know. But I can tell you that. So, and why? And here, this is kind of the, why is it so there are no paradoxes? Because it is close to human reasoning. Because in human reasoning, there are no paradoxes. We don't fill our brain going with paradox. Here's a nice thing. I ask you, are you happy? Have you ever answered, well, I'm not unhappy? Has that? It's happened to me. I asked somebody and he told me this and I already left. And this is a paradox in formal logic. Okay? Because you cannot be happy, because if you were happy, you would have answered yes. And you're not unhappy because you say, no, I'm not unhappy. Okay, so why am I doing this? Why am I talking about when I'm interested in problem solving out in the real world? Because my technology is going to be argumentation technology, and I want to give emphasis and I want to give respectability to argumentation. And that is why I'm doing this theoretical thing. I'm saying, look, don't worry, we're not abandoning classical logic. It's the same as classical logic in that specific realm. Okay. And what realm is that? I have to make sure I can defend against every attack. You have to do an extensive, complete defense against every formula that can be in contradiction with your formula, which you don't do in real life problem solving. Okay, remember the trick, and this is, okay, there are two tricks, two technical things in this proof. The one is this, that premises are stronger than hypotheses, which is obvious. This is what Aristotle means when he says, τεθέντον τινών, έτερον δι συμβαίνει εξ ανάγκης δια των κειμένων. Sorry for my French, my Greek. Okay, he says, what is a syllogism? He says, I put some things down and something else follows necessarily from them. Okay, so there is giving strength to the premises, the theory. Okay, so this, and the other thing, which is the tricky thing, is that recursive least fixed point thing that captures in the semantics, the proof by contradiction. So, but no, so what I can do now, if my premises are inconsistent, what I can do is I can extend this defense relation or this strength relation in the premises. Okay, I have two things, and I can say this I trust more than this. And this is really what's happening. Now we're going back to argumentation in AI, how things have started. So let's play a game. Okay, so now you need to think, but spontaneously, don't want too much thinking. All right? So Mary was very busy at the office. She didn't want to be distracted. Her phone rang. Will she answer? yes or no or maybe? How many yes? How many no? And the others maybe. Okay. There was a lot of people that said no because, why did you say no? Because the distraction argument is stronger than the general argument that I usually answer my phone. Now, she looked and it was her mother calling. How many yes she will answer? Mary's mother fell ill last week. She was still very ill in the hospital. How many yeses? I hope so everybody loves their mama. Right? What is happening here? That strength between arguments, let's look at it. It's context dependent. So there's the two arguments. If the phone rings, that is an argument to support answering. It doesn't mean that if the phone rings, I will answer, because there will be counter arguments. No distraction, an argument for not answering. And in the first episode, what's happening in the first episode? The second one is stronger than the first one. Look, it can defend, but not the other way around. In the second scene, they are starting, well, I may be distracted, but okay. And then here, the defense has changed. Okay. So this is kind of a little cognitive experiment to prove to you that humans reason, that we can formalize human reasoning in the large through argumentation, the thing that we just mentioned. Now, not only we can formalize it, but we can go ahead and generate technology by it. As I said, this defense or strength relation between arguments is dynamic and context sensitive, as we just saw there, all right? Mom comes into the game and the things starting to change. Illness comes in and the things starting to change, all right? Okay, so when we are deciding about what option to do, answer or not answer the phone, we need to decide on the strength at any given situation. Okay. So how are we going to do this? And this is part of the reasoning. How are we going to make it part of the reasoning? And the answer is very simple again, via argumentation. So not only are we going to argue about the object level options, answer or not answer, but also we're going to argue about the strength of the arguments that we have brought in to consider answer or not answer. Just like they do in the court with law. You don't only give the law that supports innocent and guilty, but the lawyers will argue about the suitability and the strength of their laws. And they will say, lex posterior, this law was passed afterwards, is stronger than your law. Or it's a federal law, is stronger than state law, all right? So therefore, if you can apply the priority or the strength is also becoming an argumentation arena, is an extra argumentation arena. And that is the argumentation arena that we have been developing in this system called Gorgias, which is an argumentation technology we will talk about in a moment. So basically, okay, in the same way we have premises to decisions, we have premises to priorities between argument schemes. All right? And so therefore, now this thing here becomes a set of priority arguments. Okay, this is extended a little bit to include the conflicting between opposite priorities here. So these are argument schemes, they go here, and the Gorgias, therefore, argumentation scheme is this. And so therefore, arguments now come as pairs, if you like, object level arguments for a position plus priority arguments that try to give strength to the arguments in O. And what is the attack and the defense? The defense is the beautiful thing. The defense says that if you can defend against an attack, if the attack makes with his priority arguments something in the attack stronger than something in you, then you also, with your priority arguments, make something in you stronger than something in the attack. So if you go through this little logic here, it means you can defend if either you got something which is stronger in the than something in the attack, or we're at the same level, we don't have any comparison, or if you have something stronger, I have something. Okay, so this is kind of the most, let's say, open and defense relation. And in fact, this has been introduced in 1992, and it's been unbroken since, in the sense that we've used it in many, many different problems, learning problems, reasoning about actions and change, agents, deliberation, and things like this. And we didn't find any reason to change this basic definition. So it remains unbroken since then, and is ending up now to be supporting our argumentation technology. And there are two possibilities here. One is Raison, which is a French word. And this is the platform that the company in Paris is promoting. And another one called COGNICA. Right. All right, so I'm going to tell you about those two technologies in a moment. But now I want to go back and say, okay, if I've convinced you or semi-convinced you, human reasoning and problem solving in human reasoning, natural language, it really depends on this strength relation between arguments. To identify arguments is not so difficult. And there's an area called argument mining that identifies arguments and identifies the conflict relation between them. It's been going on for some time. But where do these preferences, this strength relation comes? Some of them are common world knowledge, like in the Mary phone example. We sort of, everybody's kind of mind has been conditioned to that, all right? The second group is a very interesting one. There are general priorities, general preferences in human reasoning. For example, that specific arguments that are more specific than general arguments are stronger. Okay, you can say all French like wine, okay? But then you say French people from Massy, they like beer, somehow it happened, okay? That is a stronger argument. If you get a French person from Massy, that argument will be stronger and you will decide that, okay? So that pragmatic arguments are stronger than motivational arguments, okay? She's going to go to the library because she has an essay to finish, okay? That's a nice argument. She has an essay, suppose she's going to go. The library is closed. She's not going to go to the library, and the pragmatic argument will win, will be stronger. This idea in mathematics that we have necessary conditions are stronger than sufficient conditions. Causality is stronger than persistence if we're talking about reasoning in time and in change. Okay, things persist in time. Okay, but if something happens, Newton's kind of thing, then it changes. So there are these general preferences. And then there is the third one, the third category of where do these strengths come from. And this relates to problem solving. And this relates to policies, decision policies that are specific to a certain problem, whether it's a legal document, whether are medical guidelines, whether it's a decision policy of some organization or some personal decision policy. Okay. All right. And therefore, we have these two major challenges. The first major challenge is this theoretical scientific one, if you like, that relates to general preferences in human reasoning. Is it really possible? Can we capture all preferences of human reasoning via a set of general human thinking preferences of the second type that I've said before? This is a nice scientific problem. You can look at it both formally, you can look at it experimentally, and whatever. And the second one, which is a more practical one, how in the third source, which is through policy text, how do we extract the specific preferences from policies in natural language? And here, these technologies that we're mentioning here are technologies that address this second challenge. Actually, the second one addresses the second challenge by addressing the first one a little bit and getting some kind of partial information to guide how we're going to do this. Okay, so I'm not going to tell you about the company in Paris because it's here. Our CEO at Poly, Professor Moraidis, is in Paris de Garde. I don't know what it is for now. Okay, you can contact him. You can bring him here again to give you talks. You can visit him at the university. You can visit at the company if you want to know about company. You can also go to the website. All right. But basically, the Raison tool that is we are now promoting and is out in the market, and you can use it. It's basically an authoring tool that allows you to input your preferences in your policy text. So therefore, you can't just take the policy text and throw it in as natural language and get something, but you work a little bit hard. There is a methodology that this authoring tool follows and helps you do this job. It's not difficult. And then you get an automatic translation into the argumentation framework. So in other words, you write down these preferences and you've got your system that decides based on these preferences. Okay, so as I said, go to the website. Here it is. Go to the website. We have tutorials. We have extra tutorials if you want to know how to use it and how to develop your system that follows the specific decision policy that you have. And you can use that as a module inside a bigger box because there are APIs that will allow you to have that decision module in a bigger box. Okay. We've used this already to solve this problem, which is medical data access according to European and Cypriot law. There is a piece of law that we need to follow for this to give access to medical files, and it's a very easy job to do for us who know obviously the methodology and the technology underneath. And the important thing is that once you work in this way, although you have to work a little bit to put in the law in terms of these preferences, which is not difficult because the law says generally no one has access. The owner has access to its file unless they're critical tests when he has suspended that. And the suspended access goes to full access after the doctor has discussed the critical test with the other. Okay, so this you can just put in, and what we claim is that when the law changes, the effort that we need to update our software is of the same order as the effort that the lawyers need to update the document, because it's so modular in such a thing. Okay, so we said about that. So let's, so we're now looking at this problem of, okay, I have a policy text, I have of my own company, and I want to extract the preferences from there. All right, and the answer is, and so here let's enter LLMs. So the question is, why not extract the reasoning from LLMs? Why do you want to extract something else? Why don't you just let the LLMs do the reasoning? But there are a lot of buts. do they really exhibit human-like underlying reasoning for the results? The LLMs know a lot of reasoned results, but they don't know how to reason to them, although they will give you again another superficial explanation. There are problems. I don't know if you've seen this pedantic understanding of LLMs. I don't know if you've seen this emergent misalignment issues that you go to train it on a very specific problem and you get ethical misalignment, broad misalignment. This paper is from the Nature journal, very recent. So instead of letting the LLMs do the reasoning, use them what they're good at, which is handling language, and use them as an NLP tool and taking a neuro-symbolic approach with a hyphen. Do you know what's the difference between hyphen here and no hyphen? This is a loose coupling, okay? So this integrates with a symbolic reasoner, whereas without this, you're trying to, in the neural architecture, you're trying to reproduce the symbolic reason, okay? So that is a difficult problem. We're doing this very simple thing to put things together. Okay. And to put these things together, we have found out from our understanding of human reasoning through argumentation that there is something very interesting that we can do, which is the following. Instead of connecting the natural language document to the raw, let's say, Borgias or technical argumentation framework, we will connect it to a theory of human reasoning through conditionals by these renowned cognitive scientists, Laird and Bryan. And so that when we connect it to these conditionals, we know from these conditionals how to translate that into an argumentation. So COGNICA, which follows this cognitive argumentation framework, is a symbolic machine that reasons via argumentation in a controlled natural language. Okay. So you're asking, okay, but now what are we going to do? We're going to have our document policy in this controlled natural language? And the answer is no, not necessarily. We're going to use the LLM to take the document in free natural language to translate it in this controlled natural language. So let's see. And this is where, okay, this cognitive argumentation, as I said, the theoretical basis of it has been validated quite extensively through these standard human reasoning empirical data that you have to examine if you're doing psychology of reasoning, human reasoning in cognitive science. So what we do is this. So you have the decision policy in natural language. We use an LLM to translate this into a controlled natural language of conditionals, and we'll see an example in a moment. Then the important thing about this is that it is both human readable and machine readable. Why is it machine readable? Because there is a standard canonical translation into argumentation. We can get our argumentation reasoner to reason, give us answers with explanations. These explanations, we had this system at least 10 years ago, or maybe less, 6, 7. These explanations we used to generate in structured natural language, in kind of robot-like natural language or logical natural language. And then we can use an LLM to express it in a more natural form. Going from here to here is a trivial problem. You don't need to train the LLM. You just say to it, rephrase the explanation in more natural form, and it's got 100% reliability. And the reason, because this explanation is logically formed and it recognizes the logic. Okay, good. But very importantly, the human owner or the human developer is there, okay, and is able, it oversees the whole process and is able to give feedback, all right? And either change the policy here because it's readable in control natural language, or change the policy here, its original policy, by understanding, because of the reasoner, by understanding that, maybe I had some ambiguity or I had some anomaly in my requirements and I want to get rid of them. But the main reasoning is done here. Okay. Right. So here is this control natural language of COGNICA. Look how simple it is. At the moment, I mean, we are debating whether we should add extra forms of language here or not. This is the same question: are there general preferences that can capture any preference in human language? So these are the ones. They have in the if then, only if, they have this exception, if then, conclusion, unless condition one in such cases that. They have modalities, maybe and always. Okay, and that's it. Right. So now we dare do a demo. So to do a demo, we come out. We go there. So here is a policy, a personal policy. I'm still connected. Okay, here's a personal policy about what kind of things I want to work, dishes I like to eat. Actually, we had an application during COVID. We had an application that was doing this, because then in most restaurants the menu was readable on the thing, and there was a company in Cyprus, and we connected with that company, and so you could put in your personalized preferences like this, and then when you went in to see the menu, you saw the menu annotated with green, red, and yellow. Red meant you should probably avoid it. Green is a good choice for you, and yellow is a kind of interesting. Perhaps this is an interesting thing. It's not something that you would normally choose, but it's interesting. But that stopped because, unfortunately, in Cyprus, people went back to ordinary health. Okay, so I'm allergic to nuts. I tend to order dishes with pork, etc., etc. Okay, so I do that. And this is where we hope that the demo goes all right. So now what I'm doing now, I'm asking the LLM and to translate this into this conditional natural language. Okay. With prompt engineering and things like this, things that I really don't know about, because this is what Adamos, the student, is good, and is doing this. Okay, and we got that. Right? Now that's readable, and you can start on the exercising. Say, is this really capturing what I want to do? But okay, so now that I press this, and now this is translated into Warrior's argumentation framework that can be run under the Warrior's thing. So let's just run a prediction. Let's just run a case. So we come across this dish that, let's say, contains pork, and it's not spicy. Will I order this? Let me turn this off, and I'll tell you what that does later. Okay, so now it's decided is using the policy to decide. Okay, what do you think is the answer?
Probably yes.
Okay, so you agree with chat, but you don't agree with COGNICA. I hope, if this is what they say. Let's see. The answer is maybe. From COGNICA, the answer is yes. From chat, okay, chat 3.0. Why is it maybe? Here's the explanation. Because of the assumption it may contain nuts. This was a tricky thing. Okay. Oh, you look at that and you say, oh, yes. But you say, okay, all right then. So let me have a look. So you ask, does this contain nuts? And the waiter, or you see in the thing that this, what does this contains nuts? So let's do again. What do you think is going to be answer now? No. The answer is still maybe. The chat will say no, I think. The chat no. The answer is maybe. And it tells you, because you told me you like pork, there's an argument that supports pork. There's an argument that supports yes, because it's pork. There's an argument that supports no, because it has nuts. But you haven't told me about the strength. And you say, what are you talking about? I've told you about the strength. I've told you that I'm allergic to nuts. Look how it translated. If dish contains nuts, then avoid dish. It didn't give the right strength to it. Okay. And we've been trying, okay, so do we really expect the LLM to understand? So this shows you a weakness of the LLM reason, okay? So what I can do now as a developer, I can say, yeah, all right. I know, he says. I had this prepared, okay? I'm going to change my policy. All right. And I'm going to tell it, I'm allergic to nuts, and dish with nuts must be avoided. Okay. So let's see what happens next. I'm not sure. I don't think I need to. Right. So now what has he done? He's added the modality there. Okay. Why am I showing you this example? I'm showing this example because, look, I am trying to tell you, here is a framework where you can develop real-life applications from your own organization policy. The organization here is myself and my personal policy. Okay. The organization before, as we said, was the medical access files things. So now if I do this, and I go to prediction, and we do the same thing. It contains pork, as we said. It's not spicy, and it contains nuts. Will I order the dish? And maybe. Right. Good. I like the fact that you get this surprise. Maybe. Why? The version of COGNICA, behind there are things you can do to ask COGNICA, the reasoner, to be cautious, extra cautious, etc. So the version of COGNICA that I'm bringing, using apparently, is the ultra cautious one. Okay, and the ultra cautious one, okay, says that you may be at a restaurant down the beach, and this thing may be a fish thing, and you like to eat fish by the beach and things like this. Okay, so obviously there is an issue here, but you can use versions of COGNICA which are cautious against this modality, only against these modality things, and give you the thing you expect here, the no. The other thing I want to show you, see, you can rephrase, you can call the LLM and rephrase, and you get a much more natural way that you can pass easier. Okay, so therefore here, as I said, well, just do this just for the fun. There you go. The answer is no. And it tells you that the reason is stronger that not to order it because it has nuts. Okay, good. So we can now close this completely. Now, the important thing again with this slideshow from current, the important thing is that Cognica here as what you see here is just a web interface. As an engine has an API, and you can again send to it queries like this and get answers and things like this. And therefore you can develop a, there's a video where you can see how to use this, this machine. And we have developed, again, another real-life application very recently, a real-life application for medical support using Cognica for medical diagnosis, imaging support, in other words, what image scans you need to do, treatment support for a rare disease called schwannomatosis, based on these official guidelines, ERN Centuris, whatever that is. One of the important aspects of this is these assumptions that it does. These assumptions are bringing up information either to the patient or to the medical practitioner that you need to go and check and find out about before you take a decision what treatment or what medical test to do. So this has gone through one trial of evaluation, and now we are preparing a second trial of evaluation, hopefully with a hospital in Barcelona, because that's where, I can't remember why, because the student, or the students, the two students working on this, have some connection and things like this. Okay. Oh, why have I gone out of that? So we've done the demo. Yeah. Okay. So I'm going to close in 5 minutes, if I may. Okay. So in a sense, this Cognica symbolic, the Cognica symbolic reasoner, which remember is a reasoner that reasons on controlled natural language. Okay. But how does it reason on controlled natural language? By translating it canonically into an argumentation framework of Gorgias. In a sense, this is a lens into the LLM's reasoning. We saw there that it couldn't capture the allergic preference just by saying that you're allergic. You need to be more explicit and say you must avoid these things, okay? It's a lens. And in a sense, it's also a lens. It's a kind of experimental tool. It's a microscope, if you like, into actual human reasoning in natural language, especially when you connect it with these mental models of conditional reasoning as we have after. So now currently we're doing different types of experiments between Cognica and LLM. We're comparing their answers systematically on big data sets. We're comparing the explanations that they give. It's not just whether they give the same answer, whether they give the same explanations. We are comparing kind of the synergy that they can have, as we're seeing in this LLM-COGNICA pipeline. We are actually generating also data from Cognica, training data to fine-tune the reasoning of an LLM. But these are kind of experimental studies that we don't think they are going to, they're more for that first challenge, the challenge of understanding the scientific problem of understanding what is reasoning. Okay. The second challenge of actually doing problem solving, I think we are ready because we are not going to fall into this trap of wanting to automate everything. We want to keep the human there on the side, as I tried to demonstrate in the demo. Okay, the human should be there. We give tools, we're generating tools to understand what this policy says, and to help the human not only understand, evaluate whether the system captures the policy, but also to understand their own policy. Okay, because many times we find out that human policies have either ambiguities or they have anomalies and things like this. I promised learning and ethical behavior. We haven't got much time. I'll just tell you two things. We've used argumentation for explainable machine learning. The important message to say about learning is the following. When you are doing learning, you are by definition in a divisible setting. There is no point in insisting that you generate a theory that has strict logical reason or strict prediction, etc. Okay. By definition, you don't know. Your data has problems and you don't know. Or you are, and the data may be okay, but you are learned. Okay. So therefore, when you take this point of view, your prediction should be allowed to have dilemmas to say, look, I can't give you a definite prediction here. I can tell you A and B are two possible predictions, and I compensate for that dilemma by giving you the explanations that support each case. Okay, all right, and I can go further down with that. So then you understand that when you're doing learning, you got to learn explanations just as much as you got to learn prediction. You've got to learn explanations. So that's the thing. And for ethics, again, ethical norms or guidelines. There are no norms which are strict. Okay. If you want to capture value alignment, moral alignment, it's better to capture it in some divisible framework that has this flexibility, and argumentation is what to do. Right, conclusions. Here's a very simple observations. Problems, any problem that we want to solve in AI or in computing are expressed under human reasoning. We don't have kind of an alien thing that comes and tells us what is a problem. The document, whether it's a one-page document or a 100-page document, the EU Act, it's written and the problem is specified under human reasoning. So if you want to have tools that help you solve these problems, it's obvious that if you have tools that carry out their processing closer to human reasoning, like argumentation, you have an advantage. Okay. And the important thing that I just mentioned, these days, from AI, the message that's coming is that your task is not to generate solutions. Your task is not to find the greatest common divisor. Is to give me an explanation why this is the greatest common divisor. Okay? Okay, in mathematics, because it's so strict and so etc., it may not be necessary. But in mathematics also, you need the proof. Okay? So, explanations are the solution. Okay? So when you're designing a system, design a system to generate explanations, not as an afterthought. Okay, I'm going to find the solution and then I'm going to tell you, explaining to it. Okay. because if you're designing to generate explanations, you're actually pre-generating the solution as well. All right. Okay. Oops. So I translate this as follows, that the usefulness and reliability of AI systems is best coming from the involvement of the human developer, the human user. It's he or she that guarantees up to a certain extent the reliability. And after all, what is reliability? Reliability is that you're close to what this person is expecting from the system, or this organization is expecting from the system. So it's that, and their ability, the systems, their ability to be explainable. Why? Their ability to explainable so that they can have this natural connection with the human. And this ability to generate explanations has to be argumentative explanations. What does argumentative explanation mean? It means coming from argumentation, as we said, but it means also argumentation explanations that the human user can argue with. Okay, so you tell me what are your beliefs, you tell me what you think is stronger, why this is stronger than that, and things like this. So I can argue and I can contest it. So we have a paper, if you want to look, that has this title, Argumentation, the Calculus for Human-Centric AI. And as I said, it can give you reliability, explainability, and efficacy. And I'm going backwards here because I want to stress, don't think that the argumentation is some exotic kind of thing. It may be that the culture, the academic culture or the research culture sort of paints it as exotic, but in reality, it is reasoning in its full generality, whether you're doing formal deductive reasoning or whether you're doing simple or simpler human reasoning in natural language. And LLMs, for me, LLMs are enablers. They are there, they're great enablers, and they will help us really develop good systems if we can connect them with formal, symbolic reasoners in the same way that we saw with Cognica. Okay, leave this because. So here's Wargias. Wargias is this philosopher. And here are most of my collaborators for years on this Wargias argumentation and its application, as we said. So thank you very much.
You are taking questions. If you have questions, I'll